All right. Looks better than last week. Yeah, we make it serious. All right, so this for the reading I did cut out almost, I guess about 25 pages, 25, 30 pages in Chapter 6. The main reason I did that was that those pages were talking about how to, they're related to specific schematics, specific circuits. And since this is in the EE class, that's not the focus of what we're trying to learn, so that's why I cut those pages out. But you're more than welcome to read them and understand them.
Regarding the circuits diagrams, do you need to fully understand how to regenerate them, or just we look into them and that's it? For example, how the diode is working, how the transistor charging, recharging.
So the circuit diagrams that were in there, particularly the large ones, you don't really need to be able to go through and analyze those. I'm more interested for you to know what happens in the block diagrams. Okay, so I don't expect you to figure out, you know, the RC time constant or the capacitor and the resistance creating a certain bias on the transistor in order to get into the linear region, or.
It's more electronics and how it works.
That's right. That's right. And so that's why I cut out those sections, because they were more electronics than how it works. And what I believe is important for this class is to understand the basic principles behind it, and then we'll let the true EEs can work on the circuit diagrams and the circuit theory. So the first question, oh man, spelling error on the first one. Sorry about that. What are two major characteristics of a receiver? Over here, the selectivity and the sensitivity, right? And so, what are the two major characteristics of a receiver? So when you go to buy a receiver, you want to know how sensitive it is. What's the smallest signal I can receive? And then another aspect is, well, if there are multiple signals out there, how specific can it get? How selective is it? Does it have sharp filters so that I only receive one signal, because I can only decode one signal at a time with my brain? So those are the two major characteristics, sensitivity and selectivity. Draw a block diagram of a receiver. You started telling me what that was. So you've got the antenna, then what comes next?
RF amplifier.
Right, you have an RF amplifier. Right, so what I want, as a minimum, I wanted to see an antenna, an RF amplifier, a detector, and then an audio amplifier. So that's kind of the minimum. But of course, if you do a superheterodyne, then it has more stages in there. It'll be okay. All right. What is the key to superior selectivity in the superheterodyne receiver?
Constant frequency, gain frequency, specific constantly.
Right. So as you read through the text, it had a discussion in there that said that if you're varying the frequency, you're also varying the bandwidth.
But it can keep the bandwidth constant.
Right, so the superheterodyne is designed so that your bandwidth, you go to an intermediate frequency that's always the same, and maybe it's 455 kilohertz or whatever it happens to be, and then if that part's always the same, then your bandwidth is going to stay the same. So that's that's the key to the superheterodyne selectivity. What's an image frequency?
It's
Okay.
It's one that produces the same intermediate frequency as the one you desire, but it's an undesired one.
Right, because you've got the sum and difference frequencies, right? You mix two signals together, and then you get the sum and the difference, and one of those is the one you want. And if the other one just happens to be in the wrong spot, then the difference frequency might happen to fall back into the range of your IF amplifier and go through the system, and that creates a mess. So Yeah, that's the image frequency.
Is it created by the oscillation?
Yeah, it's created by your oscillator that's used to decode the signal or to demodulate the signal. And when you multiply it with that demodulating signal, that carrier signal, then it creates the sum and difference frequencies. And unfortunately, it creates all of them versus the exact one that you want.
So it's creating that in addition to the original signal.
Right, right. So instead of just creating one signal, it creates multiple signals, and one of them, sometimes one will fall within the receive band of the IF amplifier, and that's called the image frequency. What's the dynamic range?
That's the one that I couldn't.
Okay, dynamic range of a receiver. The RF signals that are out there are going to go from very small to very large depending on where you're at, right? And so what happens is you want to have a receiver that's able to handle that great big change in received amplitude. Because if it doesn't, if it doesn't receive very well at the low end, then you're not going to hear your weak signals fit. If it doesn't receive at the very high end or take care of the high end frequencies, and you'll get really lousy sound coming out of your speakers. So the dynamic range is the range of your input signal. How small can it get and how large can it get?
Can I say the ability of the receiver to multiply or amplify different signals to the level that acceptable to be detected? Or to decode it?
I guess if you apply that to the first stage, then that might be okay. Yeah. Next one. Okay, we're talking about digital communications in Chapter 7, and there was a lot of information in Chapter 7 too. So, what are three advantages of digital communications? Superior noise, superior performance in the presence of noise.
You can reconstruct, you can go from digital to analog or reconstruct error-affected signals.
So you can regenerate it, and it can support error correction. And were those the three that I picked?
Yeah.
Let's see.
This is the only three in the
In terms of noise, is it noise suppression or is it what's the right term?
It's not necessarily noise suppression. It's more of being able to function in the presence of noise. So more like noise immunity versus suppression. Well, it's a little bit of both, quite frankly, because in an FM signal, it's you get the suppression effect because of the capture. You get some suppression because of the capture effect. So let's see. So error correction, yeah, that was one that I had. And then we had noise and other impairments in the channel have much less of effect on digital than for analog, and the ability to regenerate. So, yeah, we covered all three. Okay, what are the three basic forms of a pulse modulation? Yep, you got them all. So, pulse amplitude modulation, PAM, pulse width modulation, PWM, and pulse position modulation, PPM. Okay. What is the minimum sampling rate required to recover the information signal? Right. And what else is that called? Nyquist. Right. So double the highest frequency of interest, and that's called the Nyquist sampling rate.
What was the question?
The question was, what is the minimum sampling rate required in order to recover the information signal? Okay, what is pulse code modulation? Yeah, it has the three steps, and basically it's taking your PAM, it's taking your pulse amplitude modulation, and it's translating that into a digital code word, and that's what gets transmitted across the network. That's what we use in the telecom network to transfer voice channels and so forth. So we will talk about pulse code modulation today. What's even parity?
Adding bits to better prediction.
Right. So if you've got a code word out there, right, and it's got ones and zeros in it, and if you add up all the ones plus the parity bit, what does it have to equal in order for it to be
Even or odd.
even? If they all add up, if you're doing even parity, they all have to you add up, and the result has to be even, right? And if it's odd, you know that you've got an error in there. And then the last one, what coding technique is used to protect against burst errors? What was that? No. Another thought? How to deal with burst errors? Something called interleaving. Remember coming across that? So in interleaving, what happens is instead of transmitting all the data serially, it takes the data and repositions it so that parts of the data are spread out. So if there's a lightning strike and the whole section over here gets obliterated, because you spread parts of that data out, you're able to go back and collect it together. So that's what's called interleaving. Okay, I think you guys did much better in reading the chapter, and it was a lot of pages. My wife said, "How come you're still reading?" Because there was a lot of information. Okay, whoops. Okay, receivers. Whoa, why is it doing that? That's not cool. If I do it this way, how do I advance this without advancing a whole bunch? It was working earlier. Now let's open it up again and see if I open up a second time if it will behave properly. No. Okay. If it's not going to do that, I might have to connect up using my laptop if we can't get this to only advance one slide at a time. Let's open a different presentation. Oh yeah, I guess I could just do it in slide mode. Yeah, maybe I'll just do it that way. Okay. That's big enough for you guys to see anyway, right? Okay. So here's the block diagram that I wanted to see for a receiver. Here we've got the antenna going into an RF amplifier. The RF amplifier goes to a decoder where you do the demodulation, and then it goes to an audio amplifier, and that audio amplifier makes the signal strong enough that it's able to drive a speaker. Then we've got the two characteristics of a receiver: sensitivity, where sensitivity is the minimum input signal, the minimum voltage required in order to produce a specified output, or an output that's discernible. And then we'll also talk about noise floor and the signal-noise ratio relative to receivers later on in the lecture. Selectivity is your ability to tune a single channel if you've got two stations that are relatively close to each other, but are still compliant with the FCC regulations on where they're supposed to be. Is your receiver selective enough in order to filter out the station that you don't want to hear and only receive the station that you do want to hear? So those are the two characteristics you look for. I remember when I went to purchase my first receiver from some big box store, that was one of the things that I looked at was, how sensitive is it? Because I wanted to be able to receive the weak signals if I happen to be far away. And when I did receive the signals, I wanted to only receive the station that I was interested in. One type of radio that was talked about a little bit in the book was a tuned radio frequency receiver. And those types of receivers, fortunately, they don't have those anymore. I guess you can still find them if you look around. But each part of the receiver had to be tuned in order for it to work. So it had 3 stages of amplification, and each stage had to be tuned. And so what they did is they would have this variable capacitor here, and you can see that there are actually 3 of them all tied together. And problem is I can't draw on this. But if you look at the top, here, these are also capacitors. They're called trimmer capacitors. And because each stage is going to be slightly different, even though maybe this bottom part is all the same, because each stage might be slightly different, you've got the trimmer capacitor on top so that it could all be perfect. That way you only had to turn 1 knob. Otherwise you had to turn 3 knobs in order to receive your signal. And if you didn't know what you're doing, it was really hard to bring in the signal. So that was really challenging in the early days of radio when they had multiple stages of amplification. So then, okay. So then along came the Superheterodyne receiver, which was a major step forward, and most radios still use some form of superheterodyne today. And basically what happens is you've got this receive signal. Actually, maybe I can go back and forth from presentation mode to, no, that idea did not work. Okay, so what would happen is your signal would come in. So let's say we've got a signal that's basically 1 kilohertz. That AM signal comes into the mixer. And then you've got this local oscillator down below, and that's being used to demodulate the signal. But what you'll notice the dashed line there, that dashed line means that both the mixer and the local oscillator are being varied at the same time. They're both, so when up in the mixer, it's tuning to that specific frequency, and then the mixer, or the oscillator down below, is being adjusted up and down so that when I do the sum and difference frequencies of the input frequency, it comes out to be 455 kilohertz. But in reality, when I use that local oscillator, I get more than just the 455 out. I actually get 4 different signals out. So I get a copy of the local oscillator at 455. I get the original signal that comes through, which is the 1 kilohertz. And then I get a frequency that is below, the difference frequency, which is the 455 that I really want. And then I get the sum frequency. In other words, if I add the 1,000 to the 1455, I get that 2455. So I get the sum and difference frequencies, I get my original frequency, and I get the local oscillator frequency. I get all 4 of those, and then they feed into the IF, the intermediate frequency amplifier, and it's tuned to receive the 455, and so the output is 455 and the frequencies that are nearby.
For the 1999, oscillator should be reduced or increased by 1 hertz, so the other nodes will not be increased, isn't it?
I didn't quite catch that question.
The local oscillator now is 1455.
Right.
Plus the 999, or minus the 999.
Right, so you got these 2.
Yeah, I believe, as per my understanding, that the local oscillator should be increased now.
If I wanted to receive only the 999, you are correct. The reason that this figure shows those three frequencies is probably when your radio channel is probably a few kilohertz wide. And so this would be kind of your center frequency of your channel. This will be a little bit above. This will be a little bit below. But you are correct. If you had a very narrow filter and you only wanted to receive this 999, then you would have to have decreased this by 1. So you're correct. All right. So the key aspect of this is to mix the incoming radio signal so that the difference frequency is constant, which results in the constant bandwidth that we talked about earlier.
Can I ask a question?
Sure, question.
IF stand for what?
Intermediate frequency. It's intermediate because the frequency that you actually want to run through your speakers is over here on the right. It's not shown in the picture. And this is some frequency in the middle, and here's the original. So it's called intermediate frequency. In this figure, we've got an example that shows what happens when you have an image frequency. In this case, let's say we've got 2 stations. What we really want is we really want to receive the station that's at 20 megahertz, but there also happens to be a station that is at 22 megahertz. And if we go ahead and we run that through with a local oscillator at 21 megahertz, and if my IF was filtered at 1, then I end up, it turns out that both of those stations end up coming out at 1 megahertz, because if I draw the shape of my filter, that 20 megahertz is in the center there, but that 22 is within the envelope, if you will, of the filter. Now, if that filter happened to be a super high Q, very, very narrow filter, it might be able to completely filter that out. But as you can see in this particular figure, it's probably reduced the amplitude maybe by half if this figure happened to be exact. So you'd still hear it. So the image frequency is the undesired received signal. And then the way we get rid of that image frequency is, instead of just doing like 1 stage of the superheterodyne, we do 2 stages of it. So if we do double conversion, then we're able to get rid of that second one. So here's a figure of a superheterodyne receiver that has double conversion. And as you can see, you've got the RF amplifier that you expect to be there. Then there's the first mixer, and there's a local oscillator. That translates at once. And then you go through the IF amplifier, the intermediate frequency amplifier, and it goes into a second mixer. And what it does is actually does the same thing as the first stage, but it just does it a second time. And as a result, that image frequency gets pushed out to another location. Hopefully it's outside of your filter. If it's not outside your filter, then it didn't help. So in this case, what it shows is that with a single conversion, I've got this signal here at 22 megahertz, and so it falls within my filter, so I end up hearing it, which is undesirable. But if I do a double conversion, then it actually moves it out, in this case, to 40 megahertz, and that's outside of my filter, so I'm good to go. Now, typically, when we talk about IF frequencies, the intermediate frequency is almost always lower than the original frequency. And the reason for that is that components at higher frequencies are harder to manufacture. It turns out that over the years we've got better and better in our manufacturing techniques, and so now they are starting to have the intermediate frequency be higher in some cases. So you will see both the intermediate frequency at lower frequencies, and you'll also see it at higher frequencies in some cases. So don't be surprised if you see that. you want to come up and set that for me? Maybe we'll have a solution. It's not connected to the laptop. It's all local.
Okay. I'll just disable almost like, and then maybe you can try.
Okay.
Maybe you can try.
Oh.
Okay. I guess it's not happening now. Here we go. Yes.
Stay still.
So you will be able to use this to move between the slides, and you can still draw on them, and it won't move.
No, it still moves. Watch.
Okay. Oh, maybe.
So I don't know what happened. It was working earlier
Just
today.
use this to move between the slides.
I tried that, but it still does multiple.
Yeah.
See? If I come back here and then I hit that, it still goes multiple slides. I don't know why.
Okay, I don't know. Yes, let's use this.
Okay. So here's the slide on up conversion. In some cases, you'll see that signal, that IF signal at a higher, because we now have components that that can do that now. Okay. The examples that we've done so far have assumed that there's a carrier signal in there that can use for demodulation. In a single sideband or a suppressed carrier radio, there is no sideband, so then we've got to do something about it. And what we do is we reinsert the sideband. And how that's done is there's something called a frequency beat oscillator, and that frequency beat oscillator has to be tuned into the right frequency, and if it's tuned to the right frequency, then you're able to demodulate the signal and hear it. What I was thinking about doing was going to my ham radio, which has a single sideband receiver built into it, and it has a frequency beat oscillator. And what happens is when you tune to the station, it goes, it goes up and down, and then you have to get it right to where the person kind of sounds normal. Because if you're on one end, it sounds like Mickey Mouse talking. And if you do it at the other end, it's really, really low. So the frequency beat oscillator allows you to tune it right in so the person sounds normal. And sometimes the frequency varies a little bit while you're talking due to atmospheric conditions or whatever it may be. And so you're constantly adjusting that up and down, or you just get used to hearing Mickey Mouse talking in there. But that's my ham radio. In say emergency responder radios that happen to be single sideband, they've put circuitry in there to be able to track where that is, and they do that tuning automatically. So it has an additional mixer and a frequency beat oscillator to tune it to the right signal, and then it goes through a low-pass filter, and then you get your information signal back out. Then there's another type of receiver that people like. It's called a direct conversion receiver. And basically, it's a receiver that doesn't use that IF stage. It just completely skips that stage, and it's able to mix it all the way from RF down to audio. And the reason that people like it is that it's simpler, and it's immune to image frequency. Anyway, you might see more of those. I showed this slide in an earlier lecture. This is a diode detector circuit for an AM radio. And basically what happens is if you come into the circuit, so this is the antenna comes in here, goes through this inductor. You've got a tuned circuit here, and when it's tuned to the right frequency, then that's when it's able to receive it. And then The diode here is the detector. This is the diode. And what it does is it takes this original signal. Here's the original signal that's been modulated. The diode rectifies it and cuts off half of it. In this case, it's cut off the bottom half. And so then if you, and this is a representation of the original signal, what you do is you, this capacitor here helps to bridge the gap between these points. So it looks more like this. And then if you, depending on how well you do it, ideally you want to get to this signal up here that's smoother. And then you have to take the DC bias out of it, which is this capacitor here. It takes the DC bias. So in an AM radio, the simple detector is this diode. And it's really simple. That's the advantage. But it's not very, the fidelity is not all that great because it distorts the signal significantly. So that's the AM detector. Then for FM, I believe FM's next. In FM, you've got this, slope here. And if there's no signal being modulated, it just sits right here in the middle. And then if I talk loudly, it's going to swing up and down the full length of this sloping line. If I speak softly, it'll just go up and down right there around the carrier, right? So if I'm speaking loudly and going all the way up and down, then my voltage that comes out of my detector is going to be larger. So that corresponds to the amplitude of the original signal. And then the frequency of the original signal varies. The faster this varies, the higher the pitch of the original frequency. If it varies slowly, then it was a low frequency. So if you can kind of imagine, it's the slinky toy that I showed earlier, right? Where the slinky goes back and forth along that slanted line. And so that's how FM is detected, and we call it a discriminator. They also talked about stereo radio. There are a number of different ways you could do stereo. Probably the easiest way would be to go in and say, well, let's take a double sideband AM, and then what I'm going to do is I'm going to transmit the right channel on one of the sidebands and the left channel on the other sideband, and combine those two together so that, and then on the other end I receive both sidebands and I've got a right channel and a left channel. So that would have been great. That's probably what we would have done if radio stations had not already built and used mono radios or mono signal radios. So then the FCC said, okay, well, stereo's fine. We're happy for you to do stereo, but we want it to be backward compatible. So in other words, the FCC indicated that all your FM, even though you're transmitting, though you're transmitting in stereo, all those mono receiving radios out there had better still work. So they thought about it, and they came up with an ingenious way to do it. And so when you look at this particular figure, this is the original signal here. They just transmitted both the right and left together as a monophonic signal, and those radios were just, the old radios were just fine with it. So to do stereo, they transmitted the signal, and then they also transmitted two other signals that were left minus right. And then there's some other additional signal out there, but that doesn't really have anything to do with the AM or with the stereo aspect. But the stereo aspect is transmitted in these three chunks of spectrum, and then what happens is at the receiver side, if you remember the first chunk of spectrum was the L plus R, and then you had the other chunk was the L minus R. So you come and you combine them together. So you got LSR, and over here you've got LS minus R. So that ends up with giving you the 2R, right? And then down here, then you have your L minus R, and then you add the L plus R in over here, and you end up with a 2R. So you've got your separation of your 2L and your 2R, and you're able to get it through. Pardon?
De-emphasize the plug.
Oh, the de-emphasis. I forgot what the description of the de-emphasis was, but is it delimiter? I don't remember. I'd have to go back and look. But anyway, the interesting thing is that they were able to make this completely backwards compatible with what was before. And you guys, as engineers, you'll see that quite often, where you've got to protect the people, you've got to protect the incumbents that are already there. You have a question?
There's a point where one of them has to have some kind of delay to compensate for
Yes.
Something that the other one goes, right?
Yes. So, yeah, and when you do all these functions, they don't all happen instantaneously, so there is a delay. So there's another figure in your book that does show a delay box, so that, like in this one, they would probably put the delay box right there, so that the distance between here and here and here and here are the same. Otherwise, you'll get the delay is probably small enough that unless you're really paying attention, you probably wouldn't notice it. But the audiophiles that try to buy the best music, they'll tell. Yeah, the delay is because the inverter, yeah. Okay, as part of the ability of a receiver to work well, it also has to work in the presence of noise. So you've got various noise components you have to deal with. As you recall, the wider your bandwidth, the greater the noise power, and the higher the noise floor. And so if a lower signal-noise ratio is required, you need to have a better receiver sensitivity, or you need to somehow reduce the noise floor. And the noise floor can come from noise that's outside the system and noise that's inside the system. But I think right here what we're talking about is we're talking about the noise that's actually generated internal to the system. You need to make sure that the system itself, the components are chosen so that noise is minimized. And so one way to measure that performance level is this SINAD parameter. And the idea is to have the largest signal to noise as possible. And then the dynamic range, as we talked about earlier, that's the input range into an amplifier, another typo, or receiver over which it provides a useful output. So if you got a strong signal in there and your output's all garbled, then you've got to reduce it. If your signal's so small that you can't hear it, then you've got to increase it. So it's that range in between. So the SINAD measurement, this is how they do it. You've got your receiver under test. That's the kind of the beige, orange sort of colored box there, the flesh-colored box. And they take that and they run the audio output to the meter, and they just measure how much power they get out without turning on the RF generator. The RF generator is turned off, and they just measure and see what power there is. After they see what power there is, then they connect the RF generator, and they turn that RF generator up until it has it registers an increase in power of so many dB. So if I want a SINAD of, say, 12 dB, What that means is that I found the voltage level of this RF generator. I found at what point that voltage causes a 12 dB increase in the power that's read by the meter. And what you hope is that that signal that the RF generator creates is a very small signal, because if it's a small signal, it means that you've got good sensitivity. And so with FM receivers, that number is probably in the microvolt range. Other types of receivers, maybe it's in the millivolt range. So that's how you do it. And then what happens is if you've got a receiver and you know what the specifications are supposed to be, because the specification will come with a SINAD number with it, you can go and set up your own test and verify if it's meeting the performance level. If it's not, then you know that something has happened. It might be in the IF stage. It could be elsewhere. We also have what's called an automatic gain control in receivers. Why would I want an automatic gain control in my receiver? The signal's always changing. That's right. Just a few years ago, I took some scouts with me up into the mountains over here, and we were doing what's called a fox hunt. What a fox hunt is you take a radio transmitter and you hide it somewhere, and then they take a receiver with a directional antenna and try to find where the signal is the strongest, and then they use that to find the transmitter. Well, the problem was that this particular part up in the mountains was kind of a canyon area with lots of large rocks, and the signals were bouncing off the rocks. And so as you walked, you're in an area that had a strong signal, and then a few feet later, you're in an area that was a weak signal. And that was really challenging for them to find the fox in this case. But what that would mean for you and me, if we were listening to an AM radio, for example, and it didn't have automatic gain control, you'd have really loud, and then, wait a minute, now I can't hear it. You'd be sitting there turning the knob up and down just because of how radio happens to propagate through the air. So they put these automatic gain control circuits in there to make it easier on your listening pleasure. So what happens is the radio signal comes in, and it can be either large or small. It's going to be varying all the time. And one of the tricks that they can use is they can take a diode detector, and that diode detector is going to eliminate either the top or the bottom, depending on how they've got it set up. In this example, they've eliminated the top. And so if you eliminate the top and integrate it, then you've got this varying voltage here, and what is that? 1 and 2, I guess. So you've got these voltages, but then you don't want it to be varying up and down with that ripple, because then as you listen to the person talking, it's going to be talking like this and going up and down, and it's going to be kind of annoying. So they average this signal, these two wavy signals, over a longer period of time, and if you average over a longer period of time, it results in this flat line that just slowly moves up and down based on what your received signal strength is, and then that gets fed back into the gain of your receiver and adjusted accordingly, so that when you're listening to it, it sounds like it's all staying at the same level. So, does anyone know how they there were used to be VCRs that used to record, you'd use to record your television program, and some VCRs had a special feature that would skip the commercials. How did it know it was a commercial?
Very controversial, right? That it was skipping ads. So
it depends on who you talk to. The people that were paying for the advertising didn't like it at all, right? And people that, like you and me, that just wanted to watch the program, didn't care about the advertising, well, we loved it. So one of the things that would happen is the advertisers, they would transmit, the advertisement is actually transmitted at a higher level than the regular program. So they would just, the VCR, as it was, listening to the signal, looking at the signal, if it saw a jump in the signal, it would say, this is a commercial. It would blank it out. And that's basically how it worked. Just last week, my wife was listening to, was watching a movie, and she got really annoyed because it wasn't a commercial situation. It was a situation where you had talking and then you had music. And when it switched from talking to the music, they turned the music volume way up.
Yes, or they turn it on the ads or things like that. They
Yeah.
turn it off. It's super annoying.
So yeah, she's very annoyed because it was way too loud and had to turn it down. And obviously, they didn't put the automatic gain control between the hot music.
It's intentional.
It's intentional. That one's intentional. It's not the same as what we're talking about here with automatic volume control. But I just wanted to make the point that it becomes annoying if the signal's bouncing up and down and you don't have a way to control it. So there are different types of automatic gain control. The basic automatic gain control just as the signal strength gets stronger and stronger, the reduction number gets higher and higher. Okay, which is fine, but sometimes you want to be able to amplify the very lowest signals for a while before you start reducing the gain. And so that's what this delayed is it's allowing full gain of all these lower signals here before it starts to reduce. And that's so you can hear those very, very faint signals. So a ham radio receiver might be more of this one here. And if you don't have any noise reduction, everything gets gained, or everything gets amplified. So those are the different ones. So then, if you've got this automatic gain control that's always moving the volume up and down, how are you going to know how strong your signal is that you're receiving? Your ear's not going to tell you because it's all been hidden from you with the automatic gain control. So if you really want to know, they've got what's called an S meter, and it measures between 0 and 9 is the typical S meter, and then when it gets above S meter, or it gets above S9, it's a plus 20 or plus 40 dB above S9. Yes?
Is it at any point built in? Because I was reading and it kind of said that sometimes it comes built in and I couldn't picture it.
So yes, these will come built in to certain receivers. Not all receivers have it. In fact, most commercial receivers don't have it.
I would imagine that it's kind of bulky to have it built in the receiver.
So this one actually does have one built in. And you won't be able to see it from there, but there's like a little bar down here, and the stronger signals, the bar will go farther across, and the weak signals will be weak. So it doesn't take a lot of space. This is kind of a boring S meter that's on this one, because it's just a bar that, when it gets up to S9, it goes up to about 3/4 of the way across. And in amateur radio, a lot of times they will want to know how strong is my signal, because one of the rules in amateur radio is that you should communicate on the weakest signal that you can, so that it causes less interference to others. So you're talking to somebody and you get it, and they say, oh yeah, you're coming through with an S9. You're thinking, well, that's pretty good. I could probably turn my transmitter down a little bit. If they come back and say, you're at S9 plus 20, where the plus 20 is 20 dB above S9, you're thinking, man, that's way too loud. If I'm transmitting at 1,000 watts, I might as well drop it down to 100 watts. So it helps you to know, you get the signal report, and that helps you to know how much power you can get away with, so that you can transmit the lowest power and still be able to have a good conversation going on. So that's what an S meter is used for. My other radio has, my larger radio that can transmit all the way to the other side of the world, has an S meter that's closer to the one shown in this diagram, where it has the needle, and you can visually see what that is. But that's what the S meter is for. It's so that you can see what, how strong that signal is, even when the automatic gain control hides it from your ears. Also, I'll use my ham radio receiver as an example for this as well. Some radios can receive different kinds of signals. So my ham radio I have at home can receive CW, which means continuous wave, and a continuous wave is basically a one frequency tone, might be at 1,000 hertz, and that's, if you're going to be transmitting Morse code, that's all you need is one tone to transmit. So my filters can be very narrow because I only have to receive one tone at a time. It has a single sideband. It's called continuous tone because the way you generate Morse code is that you have an oscillator that transmits at one particular frequency, and if you hold down the Morse code keyer, if you just hold it down, there'll just be a continuous tone. But as you know, when you do Morse code, you're going da 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 da, you know. But it's continuous because if you were to hold that key down, it would be continuous at that one single tone. So my amateur radio receiver can receive CW, continuous wave. It can receive AM. It can receive single sideband, and it can receive narrow band FM. So it can receive all those, but each of those has a different bandwidth, right? So let's say I decided that I was going to receive Morse code, the continuous wave, with my receiver switched to the AM mode. What would probably happen is, instead of just receiving one CW signal at a time, I'd probably be hearing about 20 of them all at the same time. And I'm just hearing all these beep, 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 all over the place. So the message here is that you want to have the selectivity of your receiver match the kind of signal that you're trying to receive. So if I'm trying to receive a CW signal, I want that receiver tuned to just look at it in a very narrow slice. If I want to receive AM, it's going to be wider. If I were to try to receive an AM signal when I'm switched into the CW mode, it's going to only have a little slice of the AM signal, and most of the components of the AM signal I'm not going to hear, so I'm not going to be able to understand it. So the key is you want to match your selectivity to the mode that you're trying to receive. Noise limiter and squelch. So when you get a lightning strike, that lightning strike is going to generate a very large voltage compared to your radio signal. And even with a limiter in there, you're going to hear that snap. You're going to hear that crack when the lightning strikes, right? If you didn't have a limiter built into your radio, it would probably just blast it out. So what a limiter does, it identifies a certain amplitude of the input, and when the signal gets above that amplitude, it just cuts it off. It limits it. And so that it protects your equipment, it protects your viewers. Squelch is a little bit different. Squelch allows you to be able to monitor a particular channel and just listen for what you want to hear. So again, use amateur radio as an example. People aren't always talking on amateur radio, but you might want to be have the radio on because as soon as someone talks, you might want to respond back to it. And while you're doing that, you don't want to all the time. You just want it to turn on when there's a good signal to be heard. So that's what this has. This has a squelch on it. If I turn down the squelch is generally variable. So if I turn it down, so now you're kind of noise for what's out there. And if you don't mind that, if you don't mind listening to it all the time, you can leave it there. But I like to turn it just above it, the point where it shuts it off. And so now, if some noise comes along, or say there's a little bunch of static, you can hear it come through just a little bit. You can hear it.
If you make it off, it's okay. You will get the signal, you will get the cut.
So now if I take it and I turn the squelch way up, now if a weak signal comes along, I might not hear it at all.
Oh, yeah.
So I want to get right on that hairy edge. And then that allows me to be able to, that allows the weak signals to come in and turns this on and I can hear it. So, so that's squelch that's based on amplitude, okay? Just the amplitude of the carrier. So when it detects noise for the carrier, it opens up and you can hear it. There are a couple of other different types of squelch. Another squelch is based on a particular tone that gets set. And if you hear that tone, if the receiver hears the tone, then it opens up. So this particular radio is tuned to a repeater that happens to be over by NCAR. And the people that operate that repeater don't want that repeater to turn on and transmit every time it hears an electrical signal. They only want to turn on when they know it's a radio signal. So what they have is they've got what's called a PL tone. What's PL stand for? Anyway, it's a tone.
Violence.
I don't know what's called that. I just call it PL tone or something. I forgot what PL stands for. So then it hears that tone, and when it hears the tone, it says, "Okay, I will open up." And that tone's like at 100 hertz or something that's fairly low, so that when you're having a conversation, you don't really notice it. So that's what it has on it. And if I talk into this, it will hear that tone, and then it will come back. So let's see if it does that. ABC or DT versus no check. So basically, that's what it did. Is like when you transmit in on amateur radio, you have to give your call sign so people know who you are. So what the repeater did is it heard that tone in my signal, and when it heard the tone, it said, "Okay, now I can respond back to you and tell you, yeah, you're able to reach the repeater and communicate." So that's another kind of squelch. It also talks about a third kind, which is a code-based squelch. Meaning if it receives a certain digital code, then it will open it up. But some of the FRS radios, the family service radios that you can buy at Home Depot or Costco or whatever, will use the codes. And let's say this one supports 32 codes, and basically what this allows you to do is allows for several, if you have multiple codes, it allows for several people to communicate without having to listen to each other. So you and I could be on using one code, and you and I could communicate on that code. to our conversation. Okay, I think this is about this is the end of this section. So why don't we take a little bit of a break. Reading through the book, it was kind of refreshing to jump from the receiving chapter to the digital coding and framing chapter. So some of the information in this next section will be information that comes from another book and may not be covered in your book to the same extent. So you'll want to probably take another look at some of these slides afterwards. And they're already posted on Desire to Learn, so you shouldn't need to worry about that. This was the one that we fixed. Let's go back and get the lecture we're going to do now. Okay. So when we go into the digital domain, we're going to start transmitting ones and zeros, and an easy way to represent that is going to be with a square wave. One of the things that I want you to notice here is that depending on the different bit sequences I transmit, I will get different bandwidths associated with that. For example, if I transmit this sequence here, where I've got 1, 1, and 0, 0, then I'm going to get something that looks like this, which will be at one frequency. Maybe I'll call that it's a period of 2, so maybe that's 1/2 of a cycle per second, or 1/2 hertz. But if I happen to also be transmitting a data sequence that's just simply 1, 0, which is this first one right here, now my period is going to be a duration of t, and that's going to be a frequency of 1 hertz, right? So depending on what my sequence of bits is, that's going to affect my bandwidth. So when I'm engineering something, I need to make sure I engineer that for the largest bandwidth that can be possibly generated through a sequence of bits, which will be this alternating ones and zeros. We have various the channels that we transmit over. We have twisted pair, and it's called twisted pair because literally that's how we make it. We have 2 pairs of wires, and we just twist them together. Sometimes they twist forward, sometimes they twist backwards, sometimes they're twisted tight, sometimes they're loosely twisted. But if I have two pieces of metal that are separated from each other, they're parallel to each other, what kind of component am I making? What kind of electronic component has 2 plates across from each other? It's a capacitor, right? What component do I have if I've got a wire that has a number of turns in it? I have an inductor. So when I have twisted pair, I've got the combination of both a capacitor and inductor associated with that. And if I twist it tightly, my capacitance will go up a little bit more. If I twist it with lots of turns per inch, my inductance will go up a little bit more. So the ideal situation is I want to the extent possible, balance my capacitance, my capacitive reactance and my inductive reactance to be about the same, so they cancel each other out. And if I can do that, then I can transmit much farther, and I can transmit much faster. When you look at different twisted pairs that you can buy, if you go down to Home Depot, you can go and you can buy Cat 3. Cat 3 is good for your telephone wiring in your house, but it's not good for data. And the reason for that is the Cat 3 doesn't have very many twists. And then when you get up to Cat 5, then you can start transmitting Ethernet up to, say, 10 megabits per second, maybe 100 megabits per second, depending on where you're at, or maybe even a gigabit per second. But it's going to depend on which cable that you use. For example, Cat5 will perform up to a certain level, and then you have to go to Cat5e, and then you have to go to Cat5 or Cat6 if you want to get the higher bandwidth. So when you go to wire up your own home with some twisted pair cabling, if you wanted to be able to transmit at the highest level possible, you're going to want to make sure you get a Cat6 cable or something like that that has the appropriate number of turns and so forth. So if you go and decide to get some cabling off of Craigslist, somebody's giving it away, and they're giving you Cat5, and you're thinking, oh, this is great, this is free, and then you realize, oh, it's only Cat5, I can't do my gigabit Ethernet on it because it doesn't have a high enough twist count. So you have to be, pay attention to the different categories of twisted pair. Then we have a coax, and coax, of course, is that single conductor with a dielectric around it and then a shield around that. And it's nice because it is more resistant to noise than twisted pair is. You can also get shielded twisted pair, which helps to reduce the noise for twisted pair. But coax, because that distance between the inner conductor and the outside shield is always constant, it has properties that far exceed those that you get on twisted pair. So as I was going through my career, and we were evolving from ADSL to ADSL2, ADSL2 plus, VDSL, VDSL2, our product folks were always getting really excited when we jumped from one technology to the next, because we were increasing the amount of bandwidth that we could provide to our access customers. And what they didn't realize is that whatever you could do on twisted pair, you can always do better on coax, because coax is simply a better medium. And as you know, there are always trade-offs in engineering. Even though coax is a better medium, the trade-off in using coax is that coax costs more than twisted pair does. And on top of that, coax is going to require some additional installation effort in order to put connectors onto the ends, where twisted pair is just like a screw-down terminal, whereas you have to put a F connector on to the end of coax. So there are always pluses and minuses. Probably the biggest challenge that the telephone network has is that it's used twisted pair for years, because that came along before coax, and then to switch from twisted pair to coax would just be a challenge for them because of all the effort to remove all the twisted pair and replace it. So basically, if I come up with a new modulation technique that doubles my throughput on twisted pair, and then I put on coax, it's going to do even better on coax. So if I were in a greenfield situation and I was just going to base my technology choice on performance, I'd probably pick coax. If I wanted to base it on cost and installation ease, then maybe I'd pick twisted pair. So you always have those trade-offs that you get to deal with as an engineer. Then we've got fiber. Fiber's great because it's very immune to noise. The challenge with fiber is that the electronics on the end are a little bit more complicated. And the biggest challenge with fiber is we don't have it all over the place. It's only in certain places. If I had my way, I would have the phone company replace all of their twisted pair with fiber, and then also attach to the end of the fiber wireless transmitters for those people that don't want to deal with any cables. So my network would be a combination of fiber and wireless. Wireless, everybody loves wireless because they don't have to worry about where do I connect my cables. They don't have to worry about ugly cables running up and down the walls. But the disadvantage of wireless is interference. It's super sensitive to noise interference. So that's the big disadvantage. But boy, is it convenient. I don't have to worry about where I connect any wires with wireless. So
Future for multi-waves.
the future for millimeter waves. Yeah. So
Do you expect that fiber?
So the question was, with millimeter wave radio coming in, will the need for fiber diminish? And what I think is probably not. I think what will happen is millimeter wave will become more prevalent, but then that wireless technology is generally just put on the end of the circuit. So it makes it easier for the end user, but then once it gets past a certain point and connects into the network, then it's easier for the network in terms of reliability and so forth to put it on fiber. So I would say that more millimeter wave radios out there means that there's going to be more fiber behind it to haul it back through the network. So I think it's going to be, millimeter wave will help drive more fiber as a backhaul behind the millimeter wave. So I've drawn a square wave here, and if I run this square wave signal down the channel, it's like ones and zeros. If I run that down the channel, as it goes farther and farther, that square wave gets distorted. It gets kind of smushed and stretched out like I have over here. And after a while, it no longer looks like a square wave. And in fact, after it gets too far out there, then sometimes the square waves, sometimes these waves start to overlap, and then you get to a point where the overlapping is so bad that you look at that point of overlap and you're thinking, well, was that originally a 1 or a 0? And that's the point that you've gone too far. The great thing about digital communications, as was reflected in your quiz, is that before it gets that far, you can always regenerate it. You can detect that signal, figure out what it was supposed to be, and then regenerate it with a brand new square wave. And you can do that over and over again, which means you can go around the world as many times as you want and not lose any data. You just have to have regenerators every so often. And I like the term regenerator better than repeater. Some people will say repeater, but repeater can also apply to analog signals as well. And in the analog world, when you do an analog repeater, it amplifies both the noise and the signal. So after a while, you can no longer amplify it anymore. But in the digital space, where you use a regenerator, you regenerate the signal and the noise is eliminated again. And then it goes down the channel for a little ways, and noise comes in, and you get distortion. You regenerate it, then the noise and the distortion goes away again. So that's the beauty of a digital system, and that's why we've made that transition from an analog to a digital networking. So this is just another figure of what we just talked about. You've got your original signal up at the top, and then after a while, those square waves no longer look like square waves. And as long as you regenerate those before they get too bad, you're good, and you can continue going on as long as you want. So this is a speech channel. And in the telephone network, their channels are between 0 and 4 kilohertz. And then the speech band, almost all of the speech components are between 33 or 300 hertz, 300 hertz, and about 3,300 hertz. And then when we talked about Nyquist, that told us that if we want to represent this in the digital domain, I have to sample this at least at a rate twice the highest component, right? So if my highest component here for voice happens to be this 3,300 hertz, then I have to at least be transmitting at I have to sample at least 6,600 samples per second. And lo and behold, the telephone network, they transmit, they sample at 8 kilohertz per second, so that's above the 2 samples per second. I found this diagram, this oscilloscope.
Sample rate. It's sample per second.
It's a sample per second, yes. It should be, to be perfectly accurate, it should be like 8 kilosamples per second. That would be the right way to say it. So just getting lazy and called it hertz, but you're right, it should be samples per second. So the sampling rate, the Nyquist sampling rate is at least 2 times the maximum frequency. If you want to play around with this, I assume that this link is still good. It was good last time I checked, but it's been a while. You can go and play with it. If you look at this link and look at the grid over here, it has a frequency of 1/2 cycle per second, which means if it's 1/2 cycle per second, my period is going to be 2 seconds. So I'll have 1 cycle every 2 seconds. So now if I sample this at a rate of every half a second, then I'm sampling it here on each of these green dots. And if I connect those green dots together, I can recreate that signal. Now, so this would be the case where I'm sampling at every half second, which is obviously higher than twice the frequency. In this case, down here, I'm going to sample at exactly the same frequency as my tone. And so if I do it exactly at twice the frequency is what I meant to say. At exactly twice the frequency, so I'm going to be sampling twice on each cycle. So I do here, 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 and here. And if I've got those sample points, I can look at that and I can say, yeah, I can generate my original signal from that. But it could still be somewhat ambiguous because I could also do it 180 degrees out of phase, and I could have created this signal, right? So that's the reason why you want to have it be greater than twice the highest frequency, because you could still have some ambiguity if you're actually equal.
When you're recreating that, how would you know the amplitude in that case?
You wouldn't. You'd be guessing. Maybe it was an FM signal. But you're right. There's not enough information here to accurately recreate that. I could also recreate it like, well, I guess if I skip some points, then I would be kind of cheating. In this third one, I'm going to sample it less than twice the frequency. And so I'm sampling at 1.5 instead of 2 times. And so here are my dots here. And if I knew what I was looking for, I could filter out exactly what I was looking for. I could recreate it. I could connect all those dots. But say I could also look at this and say, well, if here's my dots, I can create it this way. And that's called aliasing, where you're actually getting a lower frequency than what the intended frequency is. The reason all this happens is that when we talked earlier about sum and difference frequencies, some of those, if you don't sample high enough, those sum and difference frequencies, some of those will fall within your band of interest and create interference. If you could somehow come up with a filter that could notch out those frequencies that come within your band of interest, then maybe you could recover it, but it would be very difficult unless you're just doing single tones. And if you're doing single tones, that's just a question of how sharp is your filter. But anyway, that's kind of illustrative way to show what happens if you sample underneath the 2 times the maximum frequency sampling rate. This is a depiction of the word bingo in the time domain. So you can kind of look at that and imagine how that might be put together. The B is going to be louder and the G is going to be louder, right? So that's probably where the B is, and this is probably where the G is. We have B-I-N-G-O. So you've got that particular waveform in the time domain. And if I put it in the frequency domain, the frequency domain of bingo will look something like this, where I've got the largest frequency components happen to be at the lower frequencies, and so they create the peak here, and then as I go higher in frequency, they tail off. And I don't need to transmit the entire thing. The higher frequencies don't have as much information content, so I could probably just filter those off at the end and then just transmit that piece. Otherwise, I'd be transmitting, a very long tail out into the frequency domain, which is just not spectrally efficient. So I've got bingo. Oops, wrong way. And I've filtered off the edges. Looks like this one's been filtered off at somewhere around maybe 2,700 hertz. And then what I can do is I can modulate that. I can mix that so I can have it occur at 1 times the message frequency, or 2 times the message frequency, or 3 times the message frequency. Actually, when I do mixing, all those things happen to show up, but they're at different amplitudes. So in that case of filtering, here's my maximum frequency at this edge. And then I can replicate that at, say, 2 times the message frequency, or 3 times. So I can get the same multiple copies out there if I want to. And of course, when you're mixing it, you get it on both sides. So I'm going to get all these different components out there, and then I can choose which one I really want to pay attention to and filter out all the rest. So the next segment is on the different types of pulse modulation, which you guys correctly identified in your quiz. We've got pulse amplitude modulation, and pulse width, and pulse position modulation. So on the top, I've got my modulating signal, and then with pulse amplitude, all I'm doing is I'm doing the sampling so that it matches, or it corresponds to the amplitude of the modulating signal. So I get, it's just similar to AM, where I'm just looking at the amplitude. For pulse width modulation, you'll see that at the high point, I'm wider, and at the low point, I am narrower. So that's what pulse width modulation is, just varying the width. And then at the bottom one, you can see that if I'm at this 0 crossing here, then my pulse position is right in the middle of the bit time. And then if I'm at my peak, then my position has been moved all the way to the right of the bit time. And then if I'm way at the bottom, I get moved to the left of the bit time. So that's the position aspect. One of the advantages of these two down here is a similar advantage to what FM has over AM. The amplitude doesn't affect it. So because the amplitude doesn't affect it, then these two on the bottom are more immune to noise issues. This slide shows how the pulse width modulation is put together. Actually, if you look at it, this top one could be kind of analogous to pulse position, but here's our B is our message signal, and then as you can see, as we get to this high point here, I get the widest pulses down here, and when I get down to the bottom, I get my narrowest pulses. To get from a pulse width to pulse position, all I need to do is I do my pulse width first, and then I do a little trigger, and then put my pulse just right after the falling edge. Pardon?
At the end or at the start of the shift?
You could actually probably do it, actually in this one I should do it at the start, shouldn't I? Just the way that it's been drawn. Because then you can see a difference. Because on this one, as you can see, the falling edge happens to be on the bit time, so it doesn't tell me what my position is. So to your point, on this one it should be triggered on the rising edge, so I can put a pulse there. And you can see that by putting your pulses based on the rising edge, that the position of this the resulting pulse varies relative to the bit time. So I think your book does a fairly good fairly good job at explaining that. So these two, pulse width modulation and pulse position modulation, are closely related.
I remember during my lecture we studied that pulse phase modulation.
Pulse position is also the same as pulse phase. It's just two different names. It's the same thing. So we're going to spend most of the rest of the discussion talking about pulse amplitude modulation, because that's what's used in the voice telephony network. So what I have here is I've got my information signal, and then if I go and I sample this at this point, this point, this point, this point, and this point, if I do that, do those samples, then I get this line, this line, this line, this line, this line. So very, very straightforward. It's all based on amplitude, and I need to sample that at the Nyquist rate, which is greater than 2 times the highest frequency. This I actually wanted to be one slide up. But this shows the relationship between pulse width and pulse position. And as you can see on this one, if you were to do your time based on, let's see, the time's going to, I would have liked them if they had put a line down the middle of the pulse width, like this. And then you can see that the distance that this pulse is from the center line varies a little bit. So sometimes it's close, sometimes it's a little farther away, and that's the relationship between pulse width and pulse position. And the book talks about taking this signal and inverting it to be able to do differentiated pulse width modulation. Okay, so we're back to PAM. I have to go change the order of those slides a little bit. So I've got my sine wave there, and then I've at specific intervals I do some sampling. In this particular diagram, I've chosen to have all the positive actually, I could take this and this could be, say, 1,000 minus 1,000, and then I just come over here and maybe that's turns out to be a 700 there. Maybe that's a 1,000 here. Maybe this is a minus 1,000. So very straightforward. It's just a linear scale of what the amplitude happens to be. So then what comes into play is what's called quantization noise. So all of you have cameras on your phones probably, right? Anybody not have a camera on their phone? It used to be when I asked that question, one or two people would say, no, I don't have a smartphone. But now it's gotten to the point where everybody seems to have a smartphone. So when you go and get a digital camera, what are some of the criteria you look at in order to pick that camera? You got your resolution, your megapixels, right? And so if I've got a camera that has 4 megapixels in front of me and one that has 8 megapixels in front of me, which one will I likely pick? I'll probably pick the 8 one, because these days I don't care how much memory I use, because memory is almost free. But I grew up in the days of film, and I still have some film cameras, but I haven't used them for years. But I remember the first camera I had was a 1 megapixel camera, and I thought, oh, this is cool. It's not as good as my film camera, but it's 1 megapixel. I can take as many pictures as I want, whereas with my film camera, every picture counted. Every time I took a picture, I had to compose a shot, because it cost me something every time I snapped the shutter. Digital cameras come along, and then I can take as many pictures as I want, because if there's some I don't like, I just delete them and continue on. But then I have had the issue of quality. My 1 megapixel camera probably, that took pictures that were like this, like the one on the top, just not very good resolution. Nowadays, what's a typical resolution that people like? Maybe 8, 10 megapixels, or 12. If you want to be able to blow your picture up to a large size, maybe you get one that's like 24 megapixels. So it turns out that the greater resolution you've got, the better your picture is going to look. And when you have a larger resolution, the difference between one pixel and the next pixel gets smaller and smaller and smaller. So in this top example, the distance between the pixels is larger, and the larger that distance is, the more noise you get, and that's called quantization noise. So a low resolution camera is going to have lots of quantization noise. A high resolution camera is going to have a small amount of quantization noise.
iPhone 7 is 12 megapixels.
12. So we didn't even dream you could get up to 12 when I had my 1. We thought that film cameras going to be around for a while longer. That market dried up real fast.
Early make film now, and then it's hard to get. Kodak last year, Kodak shut down its
Yeah, I think real film is probably getting hard to get. I haven't even tried to get film for a long time. But it used to be that you had your choice of print film, and slide film, for whatever reason, was always better resolution than print film. And so I would always buy slide film, and of course, but slide film cost a few more pennies to develop, because instead of a negative, the slide was the positive. And I used to take thousands of pictures with my film camera, and now my film camera just sits there collecting dust. Okay, so quantization. In this example, the quantization goes from 0 for the most negative to 256 for the most positive. So very easy to say this might be a 256 here, and this might be a 128 down there, a 0 right there. You can set up whatever convention you want to in terms of what the numbering is on the side. In the case of voice, what they've done is they've split this up into codes where if it's a positive value, they prepend that with a 1, and if it's a negative value, they prepend that with a 0. So we'll go and see what that looks like in probably about 4 or 5 more slides. But here's what, this is some discussion on the quantization noise or quantizing error. These two solid lines represent going from one step to another step. Okay, and so let's say we have a third step up here, and if my sample happens to be at this point, then it gets assigned that value. If my sample happened to be over here, it would be assigned this value. So let's say my sample happened to be at this point, and it goes up to that. How much am I off by? I'm off by about almost Q over 2, right? So that's what my error is. That's what my quantizing error is plus or minus 1 over Q. So I take that relationship, and there's another relationship that says the number of levels in my system. So this, if I have, this would be like a 3-level system. I've got 1, 2, and 3. But the number of levels equals twice the amplitude divided by the quantizing error Q. And then my maximum error is going to equal, is going to be somewhere between minus Q over 2 and plus Q2 over 2. We've seen this equation before, right? This is our power equation for dB with the quantizing noise. It's the same equation, except for now it's called the signal to quantizing ratio, SQR. Same equation, but now we've got the signal power divided by the noise power. So just for some examples, say if we've got the maximum noise ranges between Q over 2 and minus Q over 2. This is what our noise is. And then there's what we call the noise probability. And the noise probability is equal to 1 over Q. That's also called the probability density of the noise. And what I'm trying to get to is I'm trying to get to what the average power of the noise is. So I do that by integrating the noise between these 2 points, between minus Q over 2 and plus Q over 2. I integrate what's under that curve. And if I do that integration and evaluate it at the endpoints of minus Q over 2 and plus Q over 2, I get this answer of Q squared over 24 plus Q squared over 24 over Q, which equals Q squared over 12. So that's my noise power, the quantization noise power. So for an example, let's say we've got a Q that's 6 volts. So I've got my intervals on my scale, and the distance between the intervals happens to be 6. That means that my maximum error is going to be Q over 2, or 3 volts. And so if I want to find the average noise power, I put that into my Q squared over 12, and it gives me an average noise power of of 3 watts for that particular example. So now if I go back to my SQR formula, which was 10 log of my signal squared over my noise power, let's see, then if I break this down, the 12 comes up. If 12 comes up, then I can pull it out using some of the properties of logs. And so I've got 10 log of 12, and that leaves this V squared over Q squared. So I have the V squared over Q squared. I can take the square to the outside and then put it out front and have 20 log of V over Q. This number here, 10 log of 12, becomes a constant, which is this 10.8. So this is my value, or my equation for SQR, and that happens to be if my voltage is in RMS volts. So RMS is root mean squared, and it's the DC equivalent power of a sine wave. So you've got a sine wave, and the DC equivalent happens to be at the square root of 2 down, or 3 dB down. This peak up here and this line there, that's a difference of 3 dB. So basically the power of, the difference between the peak-to-peak voltage and the root mean squared voltage is essentially 3 dB, or another way to put it is it's putting square root of 2 in the denominator. So I take this relationship and I solve it for, and I solve it again looking at it from the peak voltage instead of the RMS voltage. Then I put those values in, and I come up with this 10 log 12 over 2, and that comes out to 7.78. And this part back here is the same as what we had up above, except for one. This is the peak voltage. Looking at this number here and this number here, what's the difference? It's 3 dB. So that's how the 3 dB comes in. So when you work the problems, you need to be careful of knowing, am I using root mean squared voltage, or am I using peak voltage? Because you'll be 3 dB off if you choose the wrong one. So a couple of examples to illustrate. What's our time getting to be? Okay. So we've got an amplitude of 60 volts and a Q of 6 volts. Find the average SQR, signal to quantizing ratio, the number of levels, and the number of bits required to encode. So you'll see how we translate into that into the number of bits. So if we, let's see, what was my original information? Okay, so A is 60, okay. So I have, so A is 60, which is the peak voltage. So I'm going to put 60 in there, and I'm going to put, what was it, the quantizing was 6. And since I'm talking about peak, I'm going to be using the 7.78 number. So I put those values in and solve it, and I get about 28 dB. Now we've got the relationship that the number of levels is twice the amplitude over Q. So I put those numbers in, and I end up with 20 levels. So now how do I determine how many bits do I need to represent those 20 levels? Right, 2 raised to the n, right? So here's the 2 raised to the n equals 20. So that tells me that my n needs to be At least 4.3, but how many people know about fractional bits? A bit's a bit, right? I don't have any fractional bits, so I have to round it up to 5, just like you said. So n needs to be 5. What that tells me is because this number out here didn't come out to be an integer, that I've got some waste in the system, some inefficiency in the system. So I can go back and I can solve it backwards to find out, well, what would my values need to be in order to optimize my system.
So the signal to noise ratio will be better. Change its pathways.
Well, let's see. Okay, if I were to use all 5 bits, okay, let's run it backwards and see what would happen if I used all 5 bits. So I would have a 2 to the 5th, which is 32, right? Which of course is greater than my 32 or my 20 levels. So what that means is I'm going to have the same 60 volts, right? But now I'm going to have 32 layers. So now, to actually distinguish between between the two, I'm going to have a greater signal-to-noise ratio overall in order to be able to distinguish. So I've got the relationship of the number of levels is twice the amplitude over Q. So I put the 120 in, and then my number of levels is 32 now. So I solve for Q. My Q is now 3.75 instead of the 6 that we had before. And I take that Q, put it into the equation, and now my equation comes out to be 32 dB rather than, what was it before, 28? Yeah. So I require my signal to quantization ratio has to go up a bit in order to support the 32 bits. I'm sorry, the 5 levels. Okay, now if I were to do the same problem, but instead of peak voltage, I use the RMS equivalent. I have my RMS conversion that says I take my peak voltage and divide that by the square root of 2. So my RMS voltage is actually going to be 42.5 volts. I take that and put it into my equation, and because I'm using the RMS equation, I have to use this 10.8 number instead of this 7.8 or 7.7 number. I put all those numbers in, and guess what? I get 27.8 dB out, which was the same number I had before, right? Which is what we would expect. And if I used all 5 bits, I'd be using this 3.75 number for my Q instead of 6, and I get 32, which is the same answer I had before. So the point here being that this 10.8 and the 7.8, that's your 3 dB difference. And that 3 dB difference comes from the peak versus RMS, and the RMS is 3 dB down from the peak value. So it's all consistent.
So if it's all equal, why I need sometimes to use VRMS?
It just depends on what numbers you're given. Somebody could give you a VRMS, and you can say, well, I'm more comfortable with peak, I'm going to convert it to peak and do it with peak. Same answer, 2 different ways. Okay, now we're getting closer to a PCM. So PCM, pulse code modulation, is where I'm going to translate my PAM, my pulse amplitude modulation, into digital code words to transmit over my network. So in this case, I've got my range from -8 volts to +8 volts. Each one of these intervals is 1 volt, right? That means my Q is 1 volt, right? And if my sample right here is right here, then that's going to go to 111. If my sample happens to be this one down here, it looks like it's probably somewhere around a 0. So it's very straightforward. Just map it over and see what the range is going to be. So doing an example with this one, let's say that we've got a signal that's between 7 and 8 volts. So if we go back to the previous slide, between 7 and 8 volts, here's the 8 volt here, and here's the 7. So if it's between those, then my value is going to be that 111. So if I do that, let's say that decodes to 7.5 because it's right in between. And if I want the power of the signal there, I take it and I square it, and I get 56.25 watts. And I convert that to dBm, and I get 47.5 dBm. Now I want to know what is my noise power. And my noise power is going to be based on Q, which is 1 volt. So my Q squared, 1 squared is 1, so my noise power is going to be 0.083 watts, or 19.2 dBm. That means my signal to quantization, my signal to quantizing ratio is 28.3, and I can calculate that by putting the numbers into the equation, or I could simply take these two values and subtract the 19.2 from the 47.5, and I get the answer that way as well.
A is 7.5, isn't it? A 7.5. And Q is
so my A,
7.5.
yes, that's my amplitude, and my Q is the 1. Because my equation for the power of the noise is the Q squared over 1.
So the ratio function is no, it's A over Q. Signal to noise ratio. We go back.
If I go to my power, is this one right here. If I want the noise power, right here, I integrate and I end up with a Q squared over 12 because of evaluating this integral between minus Q over 2 and plus Q over 2. I get these two values and I end up with this Q squared over 12.
This is the BN, square noise ratio, SQR.
So this is just PN. SQR would be, go back to the slide we were on. Whoops, too far. So here's SQR. And this number right here is the average noise power, which is and the average noise power is the Q squared over 12. Okay? So the next thing I want you to look at is, what if my sample, instead of up there at 7.5, my sample was down at 6.5, or, well, at the minus 6.5 in this example. So my value is closer to 0 than my original one was. If I use this minus 6.5 and put it into the same equation, now my dB number is 27.1. Okay? And if I continue on that, say I get another signal that happens to be between 2 and 3 volts, my SQR is 18.8. Or if it's between 0 and 1, it drops down to 4.8. So my relationship is not a linear relationship. And what that means is that my smaller signals are going to have a different SQR than my large signals. And so if I'm transmitting something out there, my small signals are going to behave differently than my large signals. So how do I deal with that? One way to deal with that is to change my scale from a linear scale to a nonlinear scale, so that my low values and my high values all end up with the same SQR. So that's what we do in the voice network, so that your voice comes out sounding appropriately at the other end. So do I need to talk about this slide? Well, I can just quickly go through it, but this particular problem, how many levels are required to get an acceptable SQR of 26 dB at low input levels? So let's say my input level is between 0 and 1. So then my noise power, my signal power is going to be 1/4 watt, because I'm at 0.5 volts there, and I take that and put that into that equation. So I get 125 milliwatts or 24 dBm, and then so that's that one, and I calculate what the noise power is by solving for the noise power. If I solve for the noise power, I get log of 125 minus log P of n equals 2.6, which means log P of n is minus 0.02. I use 10 to the x to solve for that. So 10 raised to the minus 0.2 is this value. So my noise power, if I solve for it, is minus 2 dBm. So so now if I take that noise power, I know that the noise power equals Q squared over 12. So now I can solve for Q. If I solve for Q, the Q squared gives me 0.007. I take the square root and I get that number. Then I have the number of levels equals 2A over Q. So I now have the amplitude and I have the Q, so I can solve for L. That says I need 184 levels. And then since that's not equal to 250 or 128, I have to go up to 256. So I'm which is 2 to the 8th. So I actually am going to have 8 bits to represent that system. So my number of levels is going to be 256 levels. Now I solve for the Q. If I solve for the Q, that tells me my interval is going to have to be this small number here in order for that system to work at low voltage levels. So the point of all that was to say, hey, my voltage levels, as they get smaller, the SQR number also gets smaller. And we want to get it so that those are more equal to each other rather than declining like that. So we go from the linear quantization to a nonlinear or non-uniform quantization, and that's called companding. And those of you that pay attention to audio have come across different kinds of audio companding techniques. Used to have one that they call DBX. Dolby has some level of companding and so forth, and that's to deal with some of these with this problem. And then in the telephone network, the companion that we use in the telephone network is called mu-law, or a mu-255 coding. It's called mu-law, and that's used in the U.S. and Japan, but not in Venezuela. In Venezuela, they would use A-law. So what that means is that the people in Venezuela are special. Now, what that means is when we go to make calls to Venezuela, there needs to be an inner working function that translates mu-law on one side to A-law on the other side. But they both do basically about the same thing, so it's a very easy translation. It doesn't create any problems in the network for us. So this slide is in your book. And if I've got a larger signal, this larger here, and a uniform, if I do a uniform quantization, my representation of the large signal looks pretty decent with the green lines. My small signal, though, doesn't look so good. It doesn't have very good resolution. If I do a non-uniform quantization, where I increase the quantization at the small signals and then leave the large ones, or I make the small signals with a higher quantization and the large signals with a lower quantization, I make the small signals look better. My large signal is deteriorated a little bit, but it's I can tolerate that better because my signal is large to start with. So that's what we're doing in the telephone network, is we're taking the small signals and we are having a smaller step size for those small signals, and then for the large signals we have a larger step size, and that's the companion that we do with MU-law. So in order to do that, what we do is we have a coding that looks like this, where if it's positive, we prepend it with a 1. If it's negative, we prepend it with a 0. The code is actually 4 bits, and the segment is actually 3, but to simplify it, I've just done 2 and 2. But this could be, if I expand this back out to 4 bits, it could be something like that. So if I get a signal that comes into here, then my code would be 0, 0, 1, 1. My segment would be 0, 1, 0, and my polarity would be 1. And I'd take that sample, and this is the data that I would send over the network, and this would represent this level up here. So that's taking my PAM and converting it to CM, pulse code modulation, and this is the code I send for this particular sample. So for a nonlinear code example, it's the same thing, but now instead of my spaces being equal, my spaces are now compressed at the low-level signals and expanded at the higher-level signals. So this would be the case if I've got a 1, 1. Looks like this sample would have been, if I do that one, then I've got a 1, 1, and here's my segment. And then because I'm below the 0, this is a 1, this is a 0, and I get this code out here. So in PCM, using MU-law, 1 bit is for the polarity, 3 bits for the segment, and 4 bits for the code, and you put them all together and transmit the whole thing. Then in the telephone network, we have what's called a DS0. A DS0 is a 64 kilobit per second channel. There's the 64, and basically that's made up of 8 bits transmitted 8,000 times per second. And the reason we do that at 8,000 times per second, it's the Nyquist rate. Exactly. Right, I need to be at least double, and that gets me there. So I take, here's the 4 bits for the code, the 3 bits for the segment, and the 1 bit for the polarity. And all those go into a time slot, because I'm going to transmit this in time slots. And all those will go in the first time slot. Then if I have a second conversation, say I've got a second conversation over here, that second conversation will go into the second time slot, and so forth. And so in the telephone network, if I've got what's called a DS1, that's a large frame that has 24 of these all right after each other with a framing bit in front. So if I take and add all that up, what I actually have is I've got 8 bits per channel. I've got 24 channels. I multiply that together and add 1 for the framing, and it gives me 193 bits per frame. And then I'm going to be transmitting that at 8,000 times a second because of the Nyquist rate. And that says that a DS1 is 1.544 megabits per second. And you'll see that number all over in the telephone network for what's called a T1 rate. And if I just want to know what the payload is, I take the framing bit off of that, and my payload is 1.536 megabits per second. And the whole telephone network, all the voice channels are built using this structure. And the people that are on the mobile network, they also fall into this structure, because what happens is their voice gets captured and taken to the mobile switching center, and out of the mobile switching center, if it has to go to the wireline network, it's converted to the same PCM using mu law, and is transmitted over the wireline network to wherever it needs to go, and then it comes back out to the call-ed party on the other end. So that's what PCM is, using mu law, and it's also referred to as G.711 encoding. There's also some other encoding that's called I want to say 732, I don't remember. But anyway, this one is at 64 kilobits. There are other codes that compress it down to 32 kilobits per second. Bits per second. And when you get into wireless, they can get that compressed down to well under 10 kilobits per second. But when it hits the wireline network, it's all translated back to the 64 kilobit per second rate, and it goes through this DS0, DS1 structure. And to get more bandwidth, they just stack DS1s on top of each other to whatever rate they're able to support on the fiber or the network that they're using. We'll talk about that in a subsequent lecture. I don't know if it's next week or the following week, but we'll get into more detail on that. This is called time division multiplexing, because I'm allocating time slots, so it's time division. In this case, it's 24 time slots per frame. So in the mu law encoding, segment 0 has this range here of 0 to 31, and the step size is 2. When I get to the high end of the range, my segment is 111. My range is from 4K to 8K, and my step size is 256. So as you can see, there's a big difference between my low levels and my high levels. My low levels, my step size is 2. My high levels, my step size is 256. So graphically, it shows up like this, where as you can see, if you're close to the 0 or the middle, these dots are close together. As you move out towards the end, the dots are spread out. So graphically, that's how it maps. Okay, that's really all I wanted to say at this point for that encoding stuff. From your policy work, does anyone recognize what this might be? Yep, it's Comcast. So what happened here was Comcast, there's this back in those days, we didn't have as much bandwidth in the network. And so if you had a big file to download, maybe you're doing an upgrade to Windows, and so you had to download a gigabyte or 4 gigabytes or whatever it happens to be for Windows. That's a pretty big file. Or you want to download a movie. Now, a movie might be 4 gigabytes. And they go to download it, and it takes up a lot of bandwidth. And if the server has to download that to a whole bunch of different people, that server has to be a pretty big server. So what they did is they used something called BitTorrent. And what BitTorrent did is it said, okay, if you've got a piece of this software on your machine, and you've got a piece on your machine, you've got a piece on your machine, instead of getting all the software from the original server, I will get it from your machine, your machine, and your machine. And you volunteer to do this. You're thinking, I download this movie, and I want other people to be able to download the movie as well. But there's going to be a lot of network congestion going back to the main server, and the main server's not going to be able to handle it, so we'll use BitTorrent to help everybody out. Which, what happens is that causes a tremendous amount of bandwidth load on the access network. In this case, it was Comcast, and so Comcast was thinking, you know what? It's not really fair that these people that are using BitTorrent are congesting my network. So what I will do is I'm going to rate limit what they transmit at. I'm going to say, okay, if I see a BitTorrent in there, I'm going to scale them down. Instead of transmitting at 10 megabits per second, maybe 1 megabit per second. So they slowed them all down, and then, of course, the people that developed BitTorrent said, well, wait a minute. How come my traffic's being slowed down and nobody else's is? And so they filed a suit with the FCC, and then the FCC had to make some decisions there. And one of the decisions that was being pushed was that it shouldn't matter what application your bit is associated with. You should be able to transmit that bit across the network. People shouldn't have to see if it's a green bit or a blue bit or a brown bit. They just transmit it across the network. Well, that seems reasonable. But what wasn't taken into consideration was that when a service provider provides you with access service, that access service is based on certain assumptions. It's based that there are several people that are going to be using that same link, but they're not going to be using it at the same time. So I can be able to support multiple customers. And that's called oversubscription. In the residential world, the oversubscription rate could be 1 to 10 or 1 to 20 or 1 to 100. So you could basically have 100 users vying for that same bandwidth. In the business world, the data used is more dense, and so they might decide, I want to buy a private line. A private line means nobody else gets to use it. I get to use all the bandwidth for myself all the time. So I go and I'm a business user. I've purchased my business line, and I'm paying $400 a month for my line, and I talk to my neighbor. My neighbor's a residential user, and my neighbor says, well, I'm getting 10 megabits per second also. I'm only paying $40 a month. And the business user is thinking, well, that's not fair. He gets 10 megabits, and I subscribe to 10 megabits. How come I'm having to pay 10 times as much as my neighbor for a 10 megabit service? And it's because the residential user is not using their bandwidth 100% of the time. So as a network provider, I can serve more customers with that same amount of bandwidth. That's what a lot of people did not understand. You guys will understand it because you took this class. But people were looking at this thinking 10 megabits is 10 megabits. And so that's kind of one of the issues that is still ongoing today is when somebody buys bandwidth service, what are they really buying? If you buy 10 megabits from Comcast and 10 megabits from CenturyLink, are they the same? Do they perform the same? And the answer is...
Best case scenario you would get, but it doesn't mean that you would have it all the time.
Yeah, right.
Cable infrastructure is shared, and the DSL is dedicated.
It's dedicated. So
hypothetically, for your DSL, you should get close to a guaranteed.
yeah, DSL ought to be able to give you a better performance for the same 10 megabits that a cable would. But people don't understand that. So one of the exercises that I'm going through is working out in the industry in the broadband forum, trying to identify certain parameters so that we can call the service, or we can identify the service for what it is versus the marketing name, so to speak. So when if we can get it all set up, if 10 megabits happens to be the measure, when I say I get 10 megabits from Comcast or 10 megabits from CenturyLink, then I get the same performance. So that's kind of the ideal of where we want to get to. That's where the FCC wants us to get to. We are a long way from being able to get to that point, but that's one of the projects that I'm working on, and it's one of the things that all of you will be dealing with in your policy activities is issues like this, where the technology and the marketing names and people's expectations don't always match, and people don't realize that we're talking apples to oranges and so forth. So I think that's one of the reasons we like you guys that are focused on policy to take a course like this, is to understand the technical background behind some of these numbers, so that when you're in a position to make a decision, you can make the best decision for whatever the particular situation is. We are to our time, so let's go ahead and close here, and then next week will be the next two chapters, chapter 8 and 9, which I think will also be dense, but maybe not quite as dense as this week. And then you've got a lab due in 2 days, right? And I heard that you guys figured out whatever the issue was and got your lab to work, so that's good. And then homework's due on Friday. So have a great week. And
would you be willing to kind of mix the format to do some multiple choice or other style?
Well, I'll think about it. So the main purpose for the quiz, in my opinion, is to make sure that you guys are prepared for the class. I'm not as concerned about the value of the quiz. They will have some impact, but the bigger impact is it'll have you prepared for today's class. And I'll consider some different formats. Obviously, the format I chose was the easiest one for me, so. All right. Thank you, and we will see you next Monday. Hopefully with fewer technical difficulties.